When a region enters prolonged drought, the visible indicators are stark. Riverbeds solidify, reservoir levels recede, subsurface water tables drop below accessible depths. However, the hydrological cycle does not cease operation in these zones. It merely shifts its equilibrium. Arid environments are defined by high evaporation rates. The liquid water that once occupied surface reservoirs and soil does not vanish from the region entirely. It is transferred into the atmosphere. The absence of liquid water on the ground does not equate to an absence of water in the local environment. Standard responses to this surface and subsurface scarcity operate on a model of liquid extraction and relocation. Agricultural and municipal frameworks attempt to access subsurface reserves by drilling deeper into receding aquifers. Alternatively, large-scale infrastructure is constructed to transport liquid water from more humid regions via pipeline and aqueduct. Both methods are predicated on the assumption that water must be sourced in its liquid state, either from the ground or from distant surface bodies. These extraction models encounter hard physical and systemic limits. Subsurface water recharge rates operate on geological timescales, rendering deep aquifer depletion practically irreversible within human timelines. Distant piping relies on continuous energy inputs and uninterrupted infrastructure, creating fragile single-point failure networks. More critically, both methods are attempting to draw from a diminishing pool of liquid water. They are structurally blind to the largest available water reservoir in the arid zone, the atmosphere itself. The hydrological cycle does not cease operation in these zones. It merely shifts its equilibrium. The absence of liquid on the ground does not equate to an absence of water in the local environment. The atmosphere contains a measurable constant volume of water vapor, even in severe drought conditions. While relative humidity in arid zones is low compared to tropical regions, the absolute volume of air ensures a significant total mass of suspended water. The structural friction here is not a lack of water, but a lack of state. The resource is present, but inaccessible in its gaseous form. Harvesting this resource requires a format that bypasses liquid extraction and instead forces a thermodynamic state change, condensing vapor directly into a collectible liquid. Addressing this specific state change barrier requires localized condensation mechanisms, often referred to as atmospheric water generators. These systems operate by drawing ambient air across cooled surfaces, forcing vapor past its dew point to produce liquid. One such structural response designed for off-grid, localized deployment is a system called Joseph's Well. It functions as a blueprint for a condensed air fountain built to bridge this thermodynamic gap using minimal energy inputs, extracting water from atmospheric humidity rather than relying on subsurface or municipal liquid sources. The physics of water distribution in arid zones dictate that as surface and subsurface liquids recede, atmospheric moisture remains the most consistent variable. The constraint is not the absence of the resource, but the mechanical and energetic threshold required to change its state. The viability of water access in drought conditions ultimately rests on the efficiency of that transition.